Hi students, in the last video we talked about a read-only memory, a ROM. Today I want to talk to you about a PLA. So a PLA is a programmable logic array, and it's similar to the ROM except it does not provide a full decoding of the variables. PLA does not fully decode the input variables. And also that decoder, so in place of this, it's replaced by an array of AND gates. It can be programmed to generate products of the input terms. And this is reprogrammable, not like the ROM where it was permanent. So I'll say the decoder is replaced by an array of AND gates that can be programmed to generate the product terms. Okay, so then those products are connected to OR gates to provide a sum of products. And then finally, there's the final stage are XORs, so we can toggle between our output or the complement of our output. Okay, so that's a description in words. Let me show you a picture so it's a little bit easier to understand. So here's an example of what a PLA looks like. So suppose we have three inputs, A, B, and C. So there's this cool little buffer / inverter gate that we can use, and basically it's like we've got two outputs, and one of the outputs is on top and one of them is on the bottom, and this one with a bubble is the inverted output. So if this is A coming into this gate, then coming out of it, this would be A naught, and this would just be regular A. Okay, so this is an inverter and this is a buffer. So this is called a buffer / inverter gate. So we have one of those. This is just a nice way to organize that we're going to need an input and its complement. So those are the outputs of all of those. Okay, so what happens at this point? Well, the outputs of these guys are, let me write them bent down this way. So this guy comes down here. So that's C, and then C naught, C naught, and then we're going to need B, and we're going to need B naught, and we're going to need A, and we're going to need A naught. Okay, great. So this is like the first level. We have all of our inputs and the complement of our inputs. Now here, instead of that decoder like what we had in the ROM, now instead we're going to have this bank of AND gates. So the ANDs look like this. We're going to have 1, 2, 3, 4 AND gates, say. And the notation and the picture looks like this. It looks like this AND gate only has one input, but actually all of these are potential inputs. And this is the part we're going to program. So this is our input AND array. And from there, the outputs of these ANDs are going to go to ORs. So here's our bank of ORs. And then from here, this is going to go to an XOR, and this is going to go to an XOR. and we need to figure out there's either a 0 or a 1, and this is going to depend on if we want our output to be regular f or the complement of f. Okay, great. So this is kind of like an empty PLA, but all these areas, this area, and this area are where we can program this thing. So if we wanted to store on this a function that is, say, something like f is equal to ab naught plus ac plus a naught b c naught, something like this, then we would find the terms that we want to be ANDed together, right? So the first one is a and b naught. So here's a and b naught. So if I want these guys to be ANDed together, this is what I do. I make a connection here and I make a connection here. Okay, so this is my A line and this is my B naught line. So that means what comes out of here is the product term A, B naught. Then my second product term, this is AC, I'm going to need an A and I'm going to need a C, and that means that the output of this guy is my AC product term. Finally, this one here, I have A naught, and I have B, and I have C naught, and this guy is going to be A naught, B, C naught. And since I only have 1, 2, 3 product terms that are being ORed together, I don't need this last one here. But it's there in case I do need it. Great, so now I have all these product terms. Now these things need to be ORed together. So if I had my function f, I want to OR this guy, and this guy, and that's going to be connected here. This is going to go to our function output f, and I want this to be regular f and not f complement. So I want to XOR this with either 0 or 1. So let's just kind of refresh your memory on the truth table for XOR. So if we have 0, 0, 0, 1, 1, 0, 1, 1, XOR is only going to be true when this is 0, 1 or 1, 0. So if this is 0 or this is 0, 0 and this is 1, 1, then our outputs are going to be 0. So in other words, if I XOR something with 0, then my output's going to be whatever is on my other line. Does that make sense? And then if I XOR something with 1, then my output is going to be the complement of what's on the other line. So if I want regular f and not the complement of f, I'm going to XOR this with 1. So that's where I make that connection. And as you can see, for a framework like this, this has some options, right? I can have up to, I've got 1, 2, 3, 4, 5, 6 inputs. I have a possibility of 4 product terms, and I can have 2 different ORs here, and I can produce 2 different functions. Let me show you kind of how you would come up with how big this needs to be. Okay, so the size of the PLA depends on the inputs, we can call that n, and the number of product terms, that was these. We'll call those k, and the outputs, and we can call those m. So then that means that we would need, if we have n inputs, then that means we need n inverter buffer gates, And if we have, we're going to need K AND gates if we have K product terms, right? Because each one of our product terms comes out of the output of one of these ANDs. So we'll need K AND gates. And we will need M OR gates. So if our output M, we'll need M OR gates down here, these guys. And the size of this will be 2n times k will be the possible connections in the input AND array. Okay, so that's this thing here is the input AND array. So this thing here has 2n times k possible connections. That's the size of this grid. And then we have k times n possible connections. In the AND OR array. Okay, so this is the sum of products array. That's this thing. Call this the AND/OR array. And we will have M XOR gates. Okay. Let me show you another example. This will be example 2. Suppose we want to implement the two functions with a PLA. Let's say our functions are F1, our inputs are A, B, and C, and this is given to us in sum of min-terms notation, 0, 1, 2, and 4, and function 2 of A, B, and C is a sum of min-terms 0, 5, 6, 7. Okay, so we have two different functions here. We want to put this into a PLA. So first thing, let's make the truth table. So we have inputs A, B, C, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. And these are min-terms 0, 1, 2, 3, 4, 5, 6, 7. So then for F1, this is going to be 1 here, 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 and at 4, and the rest of them are going to be zeros. Okay, then we want function 2 to be high at min-term 0, min-term 5, 6, and 7, and we want these to be 0 everywhere else. Okay, great. So now we can minimize this function by putting it into a Kmap. So I'll have two different Kmaps, one for each output. F1 and F2 by putting into a Carnot map. So my F1 Carnot map, I'm going to have my input A on this side, and I'm going to put BC up here. So A can be 0, 1, BC can be 0, 0, 0, 1, 1, 1, 1, 0. So here's my 3-input Kmap. Now F1 here is 1 here, 1, 1, 1. 0, 1, 1 is 0. Then I have 0, 1, 1, 1, 0. Then I have 1, 0, 0, 0. Okay, great. So I transferred the bits in this F1 column to my Kmaps. Then from here I can simplify. So maybe I want to do something like I'll group that bit with this bit, and I can do this guy and that guy. Okay, so what product terms is that going to give me? So for this grouping here, this wraparound grouping, I have a not, and I have B is either 0 or 1, but C is 0, so this will be A naught, C naught. Then for this grouping, here I have B is false and C is false, and A can be either. For this grouping, I have that A is false, C is either 0 or 1, but B is false. And that's it. So I have 3 product terms here for my F1 equation. Now let's do the same thing for F2. My F2 Kmaps, I'm going to put A here, and I'm going to put BC inputs here. So A can be 0 or 1. BC can be 0, 0, 0, 1, 1, 1, 1, 0. That's my gray code. And I look at my entries in my F2 column this time, these ones here. So this is going to be 1, 0, 0, 0, 0, 1, 1, 1. Okay, great. So this bit here is kind of in no man's land. He doesn't have anything I can group with him, so he's just going to be by himself. But these guys here, I can make a group of 2 here and a group of 2 here. Remember, groups of 3 are not allowed. Okay, so this guy, what are the product terms for F2? F2 product terms, well, I have this guy all by itself. This is A naught, B naught, C naught. I'm going to have 3 terms here because I wasn't able to reduce any of them because I don't have anything to group it with. But I'll have a little bit of reduction here. This grouping here will be A must be true, C must be true, but B could be either. So this is A true, C true. This grouping here, I need A to be true, and C can be either, but I need B to be true. Like that. So then I have 3 product terms. So between these 2 outputs, F1 and F2, there are 6 different product terms, right? 1, 2, 3, 4, 5, 6. I don't have any duplicates that are used in here that are also used in here. If we do a little bit of algebra using De Morgan's, we might be able to reduce this even more before we actually make our hardware. So let's see if we can do anything fancy here. So let's take this F1, let's see, use algebra to see if we can make any optimizations. So if we have F1 is equal to A naught C naught plus B naught C naught, or A naught B naught. So if you put this like, I like to do it like this. I make this. I can make the whole thing complement, but that would be changing the function, and I don't want to do that. So I make it complement again. So now I have these 2 complements that I get to use with De Morgan's, but I'm not actually changing logically my function at all because I'm just taking complement, complement twice, so that's my original function. So now I have this inner complement that I can use on this thing here. So by De Morgan's, this is going to give me A naught C naught not, replace the or with an and. So this is B naught C naught not, and A naught B naught not. And then I still have this not on the outside. And then what else can I do? I can distribute this not to the inside of all these parenthesis terms. So within here, using this for with De Morgan's on this thing, this is going to give me A naught naught or C naught naught. Inside here, this gives me B naught naught or C naught naught. And inside this thing here is A naught naught or B naught naught. And I still have my complement on the outside. So a naught just becomes regular. This is A or C, and B or C, and A or B, whole thing complemented. Now if I take one of these guys and I FOIL it, so let's say I take this thing here, and I'm going to FOIL, back to my algebra days. This is going to give me A, B, or CB, or AC, or CC. Okay, so these are all ANDed together, and then this thing here is multiplied by an A or B. So then if I distribute this, this is going to give me AAB or ABC or AAC or ACC, or then I have my B term here, distribute that to all of these. This will be ABB or CBB or ACB or CCB. Okay, and this whole thing is complemented. Okay, so what can we do here? Anytime you have something ANDed with itself, we don't need to write both of them, we can just write one, right? So this thing here, we can replace that with just one A. This thing here, we can replace that with just one A. This thing here, we can replace that with just one C. This can be replaced with one B. This can be replaced with one B. And here's another duplicate here, C. Okay, so I now have AB or ABC or AC or AC or AB or CB or ABC or CB. Not. Okay, do we have any duplicates? We sure do. So there's an AC and there's an AC. Here's an AB and here's an AB. Here's a CB and here's a CB. And here's an ABC. 1, 2, 3, 4. 1, 2, 3, 4. Okay, so I have all my like terms with similar number of underlines. So if I have something ORed with itself, then I only need to write one of them, right? So this gives me AB. This thing here, I can just write one AC for those guys. This thing here, I can write just one CB for that guy and that guy. And then I can write just one ABC. And that gets complemented. Okay, so now we can make a, this is our F1, right? And that's knotted. Why do we do all that work? Well, look what we did. This is our F1, and before, our F1 and our F2 didn't have any similarities. But now our F1 now contains one of those that's in our F2 and one of those that's also in our F2 and one of these all complemented. So that's pretty similar. So see what we're doing is that we did some little trickety tricks over here with one of the functions to kind of like trick it to be in terms of some of the product terms of the other functions. That means that we have fewer product terms between the two functions. Okay. Let's now put this into our PLA. So our PLA is going to have inputs A, B, and C. So we're going to need A and A complement. We're going to need B and B complement. And we're going to need C and C complement. So then we can bend these down here. So this is C naught. There we go. And this is B, and this is B naught. And this is A, and this is A naught. Okay, great. So now we're ready for our AND gates. So how many of these are we going to need? How many product terms do we have between F1 and F2? So we have F1 complement is AB plus AC plus CB plus ABC. We have F2 was A naught, B naught, C naught, or AC or AB. So as long as we can reuse these product terms, we can use that between the two of them, and we can use this between the two of them. So how many unique product terms do we have? We have 1, 2, 3, 4, 5. 5 unique product terms. So then we'll need 5 AND gates. 1, 2, 3, 4, 5. Okay, great. So let's make the first one AB. A and B. So that's our product term AB. Let's make our next one AC. So, oops, that's A naught. There's A. There we go. So here's A and here's C. So that's the product AC. Let's make a CB. So there's our product term CB. And then an ABC. A, B, C. And the last one is going to be A naught, B naught, C naught. Okay, great. So, I hope I didn't leave anything out, but I think we're okay. So now we have all of our product terms. We have 2 outputs. We have F1 naught and we have F2. And so that means we're going to need 2 OR gates. So there's an OR, and there's an OR. I'll let this OR be my F1, and I'll let this one be my F2. And these guys, lastly, are going to go into an XOR 0, 1. Okay. So now what goes here? Our F1 needs to be the sum of products AB, that one, AC, that one, CB, and ABC. But this equation here is going to implement F1 naught. So that means in order to get F1, we need to XOR this with 1. So remember the XOR rules that we just talked about? If we XOR something with 0, then that's going to give us our other input. If we XOR something with 1, then it's going to give us the complement of our input. So we have the input coming in here is F1 not. If we want our output to be F1, then we XOR that with 1. That's kind of a cool trick. So then finally we have F2. This needs A naught, B naught, C naught. It needs an AC and it needs an AB. So all these product terms here for our F2, we sum them all together, and then this goes into my F2 XOR. If I want F2 and not F2 complement, then I just XOR that with 0. And these are the connections that we can program. So we've got an array here that can be programmed, and an array here that can be programmed. And that is the PLA. Let me know if you have any questions.